is part of an IMO shortlist problem, and I think the hardest part. It's a kind of an intermediate step that makes it a hard problem in my opinion. But International Mathematical Olympiad, I think back in 2003 maybe, and it was a shortlist. And I don't know if that means it didn't make it, it was almost good enough to make it, something like that, but it is from the short list. And this isn't the entire problem as it appeared on the exam, but it contains a crucial step that made that problem a challenging problem. Now we're supposed to show that 2002 raised to the 2002, which again is a huge, astronomically large number that can't be pronounced. Okay, we want to show that it can be expressed as the sum of four cubes. Now, y'all, when this is stated, it's tacitly implied that they're not necessarily distinct. Okay, so I'll put not necessarily, and you don't have to include that information, but the instructions don't preclude it being the sum of four identical cubes. Not necessarily, did I spell this right? Not necessarily distinct. Now, this is kind of a standard, I won't call it standard, but it's common. If you can represent a number two different ways, it leads to an interesting problem statement. Okay, so again, not necessarily distinct, sum of four cubes. And you see, we can rewrite 2002 as 1,000 plus 1,000 plus 1 plus 1. But that happens to be the sum of four cubes, namely 10 cubed plus 10 cubed plus 1 cubed plus 1 cubed. So what? Well, that's kind of a start. We have the base and the exponent written as the sum of two cubes, albeit not particularly exciting. They're not distinct. Okay? Now, another thing that I would have never discovered within the time constraints of a competition problem is that 2002 is equal to 667 times 3 plus 1. Now, that turns out to be crucial also from a standpoint of exponent manipulation. Notice what we do here is just one little simple step at a time. We take out one of the 2002s. This is just a well-known, this is just a kind of a trivial example of the super well-known result that a to the m times b to the m, or a to the m times, let's say, a to the n is what I'm looking for here. Okay, we add our exponents here. It's simply a counting exercise. There's hardly any, combinatorics basically. There's m objects here, n objects here. So there's m plus n objects, right? And that's the rule that got applied right here. Okay, so we took it out, and now we have 2002 times 2002 raised to 667 times 3. Okay, now that's useful because we can rewrite this using another property of exponents. I won't write it down, but it turns this sort of structure into this sort of structure right here. See here, 667 raised to the third. It's 2002 to the 667. We have 3 copies of that thing, so you can write it like this. Now here's another key step. We leave this 2002 alone, but we substitute this other piece. So you see, we've used both of these representations for 2002 to get to where we want. And now you see we have a bunch of things with the same power. Okay, so again, by the distributive property, you can, and the laws of exponents we've already mentioned, you can bring the 10 inside of here. The 3 goes away because there's already a 3 here, right, and so on, folks. So this does it right here. This is the way we do it. This is the sum of 4 cubes. Only 2 distinct numbers, but it's the sum of 4 cubes, non-distinct. I don't know what I said a while ago, but it's QED time. Okay. And again, folks, I don't know how. It's easy enough once you know where to start, right? But who would know to start here unless you were a practice competitor or you had some kind of insight into the nature of, who would know to write this down? Moreover, and then this, once you do it, it's fairly routine exponent manipulation. But how do you know to write these 2 initial conditions down? I guess that's why it's an IMO problem. But I'll write more about this problem. Again, it's a short list problem. It's part of an IMO short list problem. I'm not 100% sure what that means, but I don't think it made it. It means it almost made it, I think, to the actual competition problem. And I found it in Titu Andreescu, the Romanian mathematician from Dallas. It was in one of his books called 104 Number Theory Problems. But anyway, that does it, folks. Thanks for viewing.